All right, so my name is Julian Gass, and this semester I've been working on optimizing jet finding in the ATLAS trigger system. So ATLAS is a multi-purpose detector at CERN, at the LHC. As most of you know, it is used to study standard model predictions and also look for new physics that can't be explained by the standard model or the current standard model. Like the CMS detector, it sees around 40 million collisions per second. So in order to actually use that amount of data effectively, the ATLAS detector utilizes a multi-layered trigger system to sift through the events and look for interesting characteristics that physicists actually want to study. So my part in that is I work on the lower level trigger on optimizing jet finding. So jets, you can kind of see from this bottom picture here, they occur when two protons collide head-on with each other within the detector. And this collision creates or knocks loose one of the intrinsic particles of the protons, either a quark or a gluon. And those particles cannot exist on their own in empty space, so they decay into more stable particles, although those particles themselves aren't quite so stable, so they also decay, and it kind of causes this chain reaction of decaying particles that ends up with a sort of cone of hadrons. And this happens all before any particles reach the detector. So what the calorimeters within the ATLAS detector actually see is this circular, somewhat circular shape of hadrons. And it's an important goal of this upgrade to be able to efficiently find these jets in order to kind of see what's going on within the first instances of the collision. So my specific goal is to be able to perform anti-KT jet reconstruction at the hardware level. So anti-KT jet finding algorithm is the most popular jet finding algorithm used in ATLAS, and you can kind of see why in these plots. This is input data that the calorimeter would see, and at the bottom right you can see the anti-KT algorithm, and it gives us these nice circular clustered particles, as opposed to the top two algorithms, which are pretty snaky and don't really have a very intuitive shape to them, and cone algorithm is a little too small. So we want to be able to perform the anti-KT algorithm within a latency of 2.5 microseconds, which is a bit difficult because, as you can see here, the algorithm is iterative. In every iteration, it would either decide to merge a pair of inputs that it was given, or find an input that is isolated and remove it and declare it a jet. So this means that it requires, if there are n particles in the collision detected, then you need n steps to actually cluster them all with the anti-KT algorithm. And running the calculations on this with the most advanced hardware today, this would require around, or this would mean that the anti-KT algorithm can only handle around 32 inputs, which, as I'll show later, is far below the amount of inputs that you generally see from a calorimeter. So we have to somehow get around this. On this picture here, you can kind of see this is what the inputs of the anti-KT algorithm look like. So the axes are the pseudo-rapidity and the azimuthal angle of the particles found within the cylinder-like calorimeters, and then the z-axis is the energy of those particles. But you can kind of see from this picture here that just by eyeballing it, you can really see where the jets are. Where there are groups of high energy particles. So what we're thinking is that rather than have the algorithm determine whether this particle to the far right should be merged with the particle to the far left, which they obviously shouldn't, we are thinking that maybe we could localize this algorithm just to regions around these high energy areas. So that's what we are currently looking into. Our plan is to lower the resolution of the data from the calorimeter, find high energy areas, and run the anti-KT algorithm in regions around those high energy areas. So this would definitely reduce the amount of inputs to the algorithm, which would hopefully reduce the overall latency to manageable levels. And so we have to run analyses on simulations of anti-KT clustering to see, to get an idea of what these region sizes should be and how much we should reduce the resolution of the calorimeter data. So I began by looking into the overall feasibility of trying something like this. At the top graph, you can see this is the total amount of particles found per events. And you can see on average for particles greater than 0 GeV, there are around 800 particles per event. And since the full algorithm can only handle around 32 constituents, that's definitely far too many to consider. So, but then I looked at the average number of particles within the jets found, and that's around 17, and nearly all of them are less than 32 constituents. So this gave us a lot of hope that if we can successfully localize this algorithm, then we should be able to cluster these jets within the given amount of latency. So next, I started studying how large these region sizes should be where we will be running the localized algorithm. These are a couple of the most intriguing graphs that I found. So I studied the extent of the jets, which basically means I would look at each jet and then compare it to the furthest particle that belonged to that jet that the calorimeter saw. And the distance from the jet center to the furthest cluster, you can see from the top graph, is pretty much always around 0.4, which is what we'd expect, because 0.4 is kind of the pseudo jet radius that is set by the algorithm. But then at the bottom graph, we see that that furthest constituent usually has less than 5% of the total energy of the final jet found, meaning that if we were to maybe have a region size that was lower than the jet radius, that we might not really be influencing the amount of data that we get all that much. And so we could kind of approximate the algorithm this way. So I looked at samples of isolated jets and jets in boosted topologies, which basically means close together jets, jets within jets, really. And yeah, so now, next, I will be continuing these studies. I have to look at different samples and different variations, slightly tweaked versions of the algorithm, like rather than summing the X, Y, and Z momenta of the particles found when we merge them, just sum the total momenta of the particles and then take the position of the highest momentum particle and just look at all those different cases. Once we have determined the most efficient region size of the isolated anti-KT algorithm while maintaining below the required latency, we will compare these results with other anti-KT variants like cone-like anti-KT algorithms. And these pictures detail some of my travels. At the top is most of the group in a cruise in Paris. And in the middle is my sunset Barcelona picture from the ocean. And then at the bottom is the Amsterdam flag, because half of the group is going to Amsterdam tomorrow. Okay, any questions?
If you zoom in really close on that hill, can you see that hill?
Yeah. I didn't know Amsterdam had a flag.
Cities have flags.
Oh, cities. Okay.
I know you explained it last time, but I was wondering if you could explain in sort of intuitive detail what anti-KT tries to do.
Yeah, so it uses some complex algorithms to basically determine, it'll look at every single pair of particles, and it will basically, it'll determine which pair is the closest, and it'll then compare that pair of, that distance between that pair with the inverse transverse momentum of each particle, and it decides whether that pair is close enough together that they should merge, or if there's a particle that has a high momentum that's isolated and that should be declared a jet.
So that's what each iteration is doing.
That's what each iteration.
So when you say it's comparing the pairs, that means it's running in like n squared time. It's comparing each permutation.
Yeah. Yeah, it's a very slow algorithm, but it's what's used in offline analyses, and so we want to mimic it at the hardware level. Because right now we're using a very archaic jet finding algorithm that just looks basically at the highest energy particle found and assumes that's a jet.
Right.
Do you have, I mean, you say that this other algorithms are hit. Do you have performance comparisons between the algorithm that you're using now and KT without considering time?
No, not yet, because these analyses are to help us determine what the parameters of the algorithm should be that we're trying to do. But yes, that'll be very soon, like probably next week we'll be comparing.
This might be a very naive question, but I was just thinking, like, do you know nearest neighbor algorithm? It looks to me like that could, like, from the jet graph you showed us.
The nearest neighbor?
Yeah, KNN algorithm. I feel like.
Yeah.
What?
Isn't that also n squared?
Yeah.
It's basically, I think it's basically nearest neighbor algorithm, but with weighted with the transverse momentum also.
Okay,
Yeah.
I don't quite understand what anti-KT is.
Any other questions?